Hello, everyone. This is Rohan. I know we've been talking about streaming data into Azure for some time now. I think it was a fourth or fifth conversation. So I'm going to keep this short. I know there's food outside. I'm also hungry. I'm pretty sure you guys are also. So this will be a shorter call, but just want to talk about a couple of things that we recognized when we are dealing with Iceberg tables, when we were dealing with how to get data into Iceberg particularly, and few design choices that we took, like why did we go to the entire Kafka kind of approach, why not just do batch fully, why take a middle way out of it. So the conversation is majorly going to be around those kind of things, just giving you a little bit of context. Of course, too many LT tools. We know from the morning already. There's four already talked about, and they are all doing pretty good job. So why build one more tool? Uh, it's more about like everybody's trying to solve this, was not exactly with the simplicity in mind. So we have been like thinking about how the general solution might look like, how to replace Kafka, how to work with Kafka, or how to stream. But let's be honest, like we are dealing with lake houses here. It's not exactly meant to stream data. You should not be having, let's say, Parquet files with one row of data. You should be having something which is meant to read by the query engines. You should be having small. You should not be having small file problems. You should not be doing compactions, or you can stream into it, but at the same time you're going to be paying for it later as well. And most of these ELT tools, at least what we've figured out, at least the end-to-end or out-of-the-box tools like you buy like Fivetran, they're not exactly trying to be like Iceberg native. They're 400 sources, 100 destinations. So most of the times we saw that it was creating a little bit of problem for us when we were using it internally. And when we went to it ourselves, Kafka, Flink, Spark, Devasium, all those four moving pieces, a little bit too cumbersome for us at least to manage. So we didn't want any like too many moving pieces. We wanted to have something which is easy to use, a simple Docker, which I can just do Docker run and it does the job. It should be low engineering because I'm anyway promising a lot of engineering bandwidth on Iceberg when I'm getting in. I need to maintain the Iceberg tables. I need to maintain the metadata. I need to maintain, let's say, the query engine, governance, all of those things I'm maintaining anyway. I should not be, let's say, having a separate team to manage the ingestion of it as well. So that was the thing. Of course, schema evolution, data type change. Azure team has done an amazing job and still working on it. For example, alter tables, alter columns kind of capabilities. At this now, with the branching kind of things coming into the system, it's kind of like you can create an internal dedicated queue kind of system as well within the Iceberg. You can have a separate branch. Actually excited to see it in multiple query engines going forward. Few of them have already started supporting these branch kind of systems now. Excited to see it in the other query engines as well. So overall, what is OLake? It's a simple, lightweight CDC tool. Wanted to keep it simple, built specifically for Apache Iceberg. So you have databases on one end, which is Postgres, MongoDB, MySQL, and destination as Iceberg or Parquet files on the other end. So very simple, very similar, very pinpointed way of getting your CDC logs from these databases into Iceberg at scale. So no heavy infrastructure, no 4 or 5 tools to manage. It's a simple Docker file, which is highly configurable, highly scalable. How we'll get to know, of course, that's why I'm here. And it's open source. It's Apache 2 license. The reason I'm here. So given we were talking about high-level architecture, as I said, it's simple. So wanted to keep the diagram simple. I know it doesn't look like it. We'll double click on that in some time. But overall on the meta level, it's just 4 steps. You have source DBs, which are generating logs. You have readers, which are reading the logs. Then you have a bunch of writers which are taking these logs and committing to Iceberg. That's it. It's a two to three step process. Yeah, so let's go bunch by bunch. What are sources? What are readers doing? So we are doing this for MongoDB, MySQL, Postgres. Let's double click on each one of them, how we are doing it differently, what we are thinking. When you are, let's say, connecting to a Postgres or MongoDB, let's say using Debian or something like that, it's more or less serialized. You're reading logs one by one, and you're committing, so on. So we wanted to make this fast. That's why the first step we do is actually chunk the logs. We have multiple chunking strategies based on each database. The boxes you see here are majorly that, how you chunk the database. You have, let's say, split vector in MongoDB. It's actually a kind of like a command which you use when you want to shard your MongoDB. So it's an internal MongoDB command that we have kind of taken inspiration and use the same command to chunk the MongoDB logs for us as well. And bucket auto is very similar commands, or split via batch size or something like that. So it's majorly all of these different ways of chunking is basically to make sure you create more or less similar size chunk. We don't want one chunk to be like a 1 GB file and another chunk to be like 100 MB. We want a similar size chunk because when we are reading it and we are writing it, we want it to be consistent across the readers and writers. So that's the step one. We chunk and parallelly load the data into Iceberg. Multiple strategies, of course. There's no external infrastructure required to do this. We're not exactly using a lot of things internally. It's a simple Golang code written in an open source way which does this. And it works with Docker. Then all of these chunks that we have basically read comes into a kind of like a code framework, like a kind of like a buffer. So what we do over there is we first core framework controls the concurrency, because we don't want, let's say, lot of threads running on the databases, pushing a lot of load on databases. So we basically control the concurrency. We actually commit what we are reading, so it's entirely resumable as well. For example, you have like 1 terabyte table which you want to read. Something failed at, let's say, 950 GB. I don't want to read the entire 950 GB again, which is actually what happens when we go try to do this in-house. I'm not sure if I'm the only one who faced that, but it happened to me. So yeah, so it's fully resumable. It starts from the place it stopped last time, both at full refresh and CDC. Easy new table addition for Debian signaling, all of those things, hard beating, nothing required. If you have one more table in your collection or one more table in your Postgres DB, something like that, it's just if you want it to add. It's a simple yes or no configuration. And similarly, schema evolution and data type changes and data views are all inbuilt to make sure it's Iceberg native. For example, data queue, we are basically literally creating another table within the Iceberg. For example, if you're connecting your orders table and you have some data queue, it's going to be orders underscore data queue here, Iceberg. We give monitoring metrics, state files, everything, and we have commit control concurrency as well. So it's like we are writing this in a way that we're going to talk about it in future. So we'll double click over there a little later. We support all the major catalogs, be it Hive, be it JDBC, Glue, REST, all of them we will support. Yeah, so what I was talking about kind of like a minute back, how you can have like faster writes with exactly once. So we basically have ways in which we use a quality release most of the times at the time of writing. And when we are writing, we are basically committing after we write the entire chunk. So until unless the entire chunk is not written in the Iceberg, it doesn't get committed in our system. So we had to actually do this internally instead of use the commits from Iceberg, honestly, because some catalogs support multi-table commits like REST. They recently started supporting that. Some don't. So we actually built a system in which we can have our own internal way of committing the REST. So that way, we make sure there's a exactly once delivery both at the table and the data queue, and at the same time, we make sure it's fast as well. Well, it's an Iceberg meetup, so it will be unfair to talk about like what we are doing, especially for Iceberg. We are doing the partitioning strategies, like all the hidden partitioning, all the ways to partition the Iceberg table, right? It's all inbuilt into this. Schema evolution, branching, all of those things is inbuilt. Some are coming soon. Some are already built. There's a difference in the architecture, if you have already guessed. This is not exactly like a kind of like a traditional EL which runs every hour, or not exactly like a Kafka, which is like a streaming queue or something. This is more like a continuous batch. We continuously take the data from the database, make a batch of a certain size, and then push it. So with this, you can lead to like almost like 20 to 30-second latency. And we create much lesser problems for you at the, I would say, destination end, because then you don't need to do a lot of compaction kind of cost. Instead of, let's say, pushing data every couple of seconds, doing the compaction later, we are the one taking a little longer, but creating a better destination support. So yeah, that's the fourth thing as well, which is file sizing. You can define at what file size you want in the destination. For example, you want a 256 MB file or 512 MB file. You can determine over it here, and we basically kind of like create a buffer internally, and use that buffer to make sure that number of records read that, and then we kind of commit it. So a little bit of inspiration of this actually came from Hoodie as well, for honesty. Like Hoodie manages this kind of a buffer internally. Iceberg as of now don't really have this kind of support, so we're basically taking this like on our head. Numbers, because we are continuously reading, we are parallelly loading, we are at least 3 times faster than Debian in most of the scenarios, be it full load, be it, let's say, CDC. We are 100 times faster than Airbyte. I'm sure they must be doing something about this internally over there as well. But yeah, we are almost 45,000 plus rows per second. And full load and about 37,000 rows per second in CDC. And this is Postgres to Iceberg with a machine size of around 64 GB. So this is more or less anything we want to do fastest way of doing database to lakehouse. These are the numbers. So this is fast. This is like, that's it. Yeah. So not sure I'll be able to do the demo. Can I run the demo?
You have 16 minutes, you can do a demo.
Yeah?
I have 16 minutes yet.
Oh, nice. I'm quick. Can you guys see my screen? Let me go. Yeah. So this is the first time I'm doing this. Literally, we haven't launched UI in open source as of now. So if it doesn't work, it's going to be a blooper, but I'm hoping it works. Yeah, so simple jobs, sources, destinations, UI. Most of the times we are basically seeing people using a simple Docker file to do this. But for the folks who have, let's say, less people in engineering teams like our team, there's a simple UI to do this as well. You have sources, you determine what you want to create a source, jobs. I'm just going to go through one flow with you guys over here. Let's say. Yeah. So basically, like any other ELT tool, a lot of our friends, you determine name, port, host, the OG things, and then go next. you determine your AWS. I'm using Glue here, so AWS keys, the S3 paths, all of those things. You determine what table you want, and that's it. Determine the frequency, and that's it. You just do run, and it will run, which I'm going to do right now. That's it. And now I can go and basically run this query. Yeah. Let me do a little bit of zoom in. So you can see the UTC is here. So yeah, you can see it's like 20 to 40 UTC and it's written already. So it wrote almost 100 different records in those couple of milliseconds that we are talking about. And here's the data, nothing. So yeah, simple, run, and it runs, and you get the data. Yeah, coming back to the thing that you were talking about. Yay, demo worked. Nice.
Yeah, okay.
So takeoffs, particularly, of course, this is not exactly we have taken a little bit of trade-offs, particularly we love Kafka, we love Debezium, we love those kind of ecosystems as well. So the trade-offs with those kind of ecosystem is first, like architecture, simple architecture, single integrated pipeline, simple Docker image, one click to do all of this, fully scalable as well. Debezium plus Kafka or internally built pipelines are like little bit more more components, more engineering heavy. Latency we can go as low as like 20 to 30 seconds, or depend on your throughput. If you have throughput which matches like 512 MB files in a couple of seconds, of course we can do that as well. But most of the times we have seen like it takes at least 20 to 30 seconds to fill that 512 MB file. And latency of Debezium, Kafka, or internally built pipelines we have seen most of the times depends on your source and sink. It is not exactly straightforward to imagine how the latency would imagine that. Complexity, of course, you saw it was. I was doing this because the demo worked. And fault tolerance. This is a system actually not meant for very high fault tolerance. We have made sure that we do this fast, we do this lightweight, equally, we don't really have a big buffer for it. So if you want to have a system which has 10 days of fault tolerance for you, we have those systems. We have a simple way to get your database data into lake houses. That's it. If we're not going to have 7-day, 10-day fault tolerance for you. And you get, you trade it off with simplicity and easier architecture and all of those things. Flexibility, this is purposely built for Iceberg and databases and Kafka kind of ecosystem. We are getting Kafka as a source here and Kafka as a destination here as well. But your own internally built pipelines will, of course, be much more flexible. Schema changes handling DDLs, data type changes, adding or deleting of a table, all of those things are kind of built in-house internally in this. You don't need to manage your own schema registry in a separate Kafka topic somewhere. All of those headaches you don't need to do. And use case, of course, simple, speed, low infra of database to Iceberg. That's what we do. If you are thinking you want to go still, let's say, Debezium, Kafka, or any internally built Spark streaming kind of systems, those are really great for event-driven architectures, or you have, let's say, multiple destinations or something like that. We really are not exactly useful for that. What's ahead, particularly for this project? We'll be doing more optimizations, like how you can do clustering, how you can do all-grain, even a little bit of lightweight compaction. I was actually talking to somebody outside about soft compaction, how you can have a soft compaction when you're writing. So just to make sense, make it easier at the time of read in Iceberg. More connectors, of course. As I said, we want to have Kafka as a connector. We are even getting requests for SQL Server, Oracle's, DB2's kind of systems. A little bit of black box for us. Gonna be a challenge, but we are ready for it. And we want to write in Iceberg v3. It's coming in. Of course, we are also internally working into it. How we can get support for delete vectors, how we can get support for geolocations, all of those things. We are Iceberg native. We cannot call ourselves Iceberg native if we don't start thinking about these kind of things. Table management, observability is something that we have been working ourselves as well. This is majorly to understand, how should I say this, the problems we are creating ourselves. We are creating small files, we are creating orphan files, we are creating snapshots which needs to be managed. We are creating a lot of things in Iceberg. They need to be managed somehow by the user themselves. So we are creating a better way to observe all of these table metrics internally in this system as well. There's definitely in pipeline. Gonna take us some time, but we're gonna be there. And yeah, as I said, I'll be quick. I hope people are still hungry. So, any questions, any thoughts? Give us some stars. You can connect to me. We love stars.
Thanks for the talk. I have one quick question. Is this a tool that dump a database table to Iceberg, or is a continuous CDC service that take whatever live stream of updates also into Iceberg table?
Later. So we can do continuous streaming of your CDC logs from databases into lakehouses. For example, you have like a bunch of events, a bunch of changes of sorts happening on databases. We are working on a continuous listener. It's going to be live
soon. It's continuous service.
Yes. It can run continuously. It can run incrementally up to you. It's a simple Dockerfile, to be very honest. If you run it continuously, it's going to continuously listen. If you want to set it up with your like orchestration, like Airflow, Orchestra or something, it's going to run at a certain frequency.
Okay, that sounds good. So just a follow-up question. So I see some similarity to the DBZM connectors. So do you handle incremental snapshotting things like that?
We wanted to be honest. There was a scope which we were trying this out a little bit a couple of months back. We have created some things like incremental snapshotting and those kind of things as well. We haven't really gotten a lot of use case around it. Because we are maintaining the cursor ourselves. We are maintaining like which chunk we committed to Iceberg, which chunk is currently in read, which chunk is currently in write. We're maintaining all of those information. So it's going to be useful, of course, when we bring in incremental load as a direct instead of CDC. But as of now, it's not exactly.
So that means you implemented this connector by yourself, right?
Yeah.
Okay, thank you.
Are you guys? So yeah, my question is, I've been here all day and seen a lot of other similar products. So how do you guys differentiate amongst just, you differentiate with other tools?
So we kind of want to be like a middleway between your, let's say, your hourly running or daily running jobs, which you're going to be running through, let's say, a Spark streaming or maybe your own internal pipelines, maybe Airback or Fivetran kind of things, or you have like your own streaming kind of systems where you have like Flame Kafka or Debezium Kafka that starts Spark streaming or something like that. We are kind of like a middleway between them. We're not exactly streaming, we're not exactly batch. It's more like a micro batch, continuous batch kind of system, where we continuously listening the logs, creating a batch out of it and committing into the lakehouse. So it's much more, I would say, simpler, but at the same time, you actually are getting to a system which you can get to latencies like 20 to 30 seconds instead of committing for an hourly latency with a batch system or dealing with small file problems or dealing with compaction kind of table management kind of systems with streaming kind of systems. So it's like a middle layout, I would really call it that.
I have one question. So you mentioned that you are using equality deletes, right? What benefit do you get out of using an equality delete, especially in the case of like basically replicating a data, where when you are doing a delete or an update, each equality delete will essentially correspond to a single record in whatever file it is, right?
Yeah. So at the time of full load, of course, deletes doesn't come really into play. So that's much simpler. But at the time of CDC, just for the faster writes, we have been kind of treating equality deletes, like trying to use equality deletes. We have seen it is much faster to write, of course. And that's where we were talking about. We want to create the observability of the problems that we are ourselves creating. Like how much you have in your equality delete file, when you really want to do compaction and all of those things. So we are currently building all of those things. But at the same time, what I would say is like, if you want to really go in, let's say latency of 1 hour or so, it's okay if you don't want to use equality deletes or margin reads. You can do copy and writes, you can merge at the time of writing itself. But most of the times we have seen for the folks who really want to use this, want to do a latency much lower than that. So it's much easier to use equality deletes at that time and kind of you deal with that problem with compaction, maybe daily compaction or night compaction.
Got it. But do you have any insight as to why is it better compared to, let's say, positional delete?
Positional deletes, that's actually a good question. Equality deletes is much more lighter way of doing it, much more easier to kind of commit to the network ecosystem instead of positional deletes. For example, if I'm both updating and deleting the same row, much more easier if I'm doing it in equality deletes as compared to positional deletes. I don't need to write the entire thing. It's just simple, the simple statement that I'm doing this instead of positional deletes. And I think last month in the summit, they talked about that they want to degrade positional deletes the next versions. I think they also saw the problem with the positional deletes. It's not exactly useful. And vector deletes, we are actually very interested to utilize vector deletes as well. It's much simpler way and at the same time much more stable, at least consistently stable. Like if I'm both updating, deleting, or reading the same kind of logs, it's easier to do it in vector deletes. Hope I answered the question.
Yeah. It's not an easy.
Okay. Any other question? Any other thoughts? So that was me. Thank you.